So I've already explained to you how to find valence electrons. The chemical properties of an element depend on the number of outermost electrons, and those outermost electrons are found in the valence shell. So now the learning objective in this part is to show you how you can use valence electrons to group them or put them in the periodic table. Again, I've already explained how valence electrons dictate location of the elements in the periodic table. To remind you, the valence shell is always the outermost shell, the one with the highest value of n in the electronic configuration of an element. The electrons in the valence shell are called valence electrons because they live in the valence outermost shell. Let us see quick examples here. Case of beryllium. Beryllium has atomic number 4, meaning it has 4 protons, meaning that those are 4 positives. What we need 4 negatives because atoms in the periodic table are neutral. Those 4 negatives are the 4 electrons. Those 4 electrons are what we need to write the electronic configuration of beryllium. We go filling up 1s2, then we go to the second shell, fill up the 2s, and our 4 electrons are accounted for. Now you can tell that the first shell is filled up. There's no 1p, it's only 1s2, and that is shortened by helium for the noble gas electronic configuration, and the remaining shell is written outside the bracket. That second shell is called the valence shell, and the electrons in the valence shell are called valence electrons. Those are the ones that participate in reaction, and the valence electrons tell us that beryllium should be in the second column of the periodic table, and you see him right there where you have the blue box highlighted. It's in the second column. The numbers you see in this box, the 2 2, these two numbers here, that's the electronic configuration, 1s2, 2s2. Okay, and beryllium has 4 protons, 4 electrons. So coming back to our slides, you can tell here that the second shell is the outermost, and so the beryllium must be found in the second period. You see the beryllium is in the second row, the second period, because the outermost shell is the second one, and it's the second column because you have 2 valence electrons. Okay, so valence shell is 2. That tells us that we are going to find beryllium in period 2, and then the valence electrons is 2, meaning that beryllium is in main group 2, apparently 2a. That is the case of beryllium. Chlorine, we did the electronic configuration of chlorine before. These are the core, those are the core electrons and core orbitals. They account for 10 electrons. To repeat myself, the noble gas electronic configuration will be bracketed in neon, and then 3s2, 3p6, 3p5 will be outside. Sum up 2 and 5, you're going to get 7 valence electrons. That's why chlorine is in main group 7. And the shell number is 3. That's why chlorine is in the 3rd row of the periodic table. Is in the 3rd period of periodic table. So kind of a repetition of what I've already taught you, but to emphasize the relationship here. So let us continue to do the valence electron relationship to the group number. So we emphasize that elements in the same group will have similar electronic configuration. Similar in what way? They are similar because they will have same valence electron number. So if you look at beryllium was 1s2, 2s2, correct? in the case of calcium, it will be 1s2, 2s2, 2p6, 3s2, 3p6. Those are 18, and then we go 4s2. That makes 20. Guess how many valence electrons you have? 2. So you'll see beryllium and calcium in the same group of the periodic table, and its main group 2a. You would look at chlorine. He has a valency of 7. And then look at bromine that we did earlier. He also has a valency of 7. So you expect that chlorine and bromine and fluorine, they will all have a valency of 7, and they will be in the same column. So going back to the notes, what does number of valence electron tell us? It tells us the group number, the column. It tells us the group number, the column where the element belongs. So I agree. Elements in the same group will have the same number of valence electrons. I've shown you. Okay? The group number 1a to 2a, those are main group number, equals to the number of valence electrons in the main group elements. I've shown you. Again, if you look at an example like sodium with 11 electrons, it's 1s2, 2s2, 2p6, 3s1. He is in main group 1 and is going to be in the third period. What about hydrogen with 1 electron? It's just 1s1. So again, 1 valence electron. So you expect hydrogen and sodium, they'll be in the same column or group in the periodic table. The exception is helium. Helium has 2 valence electrons because the electronic configuration is just 1s2. But we put helium in main group 8, same as neon and argon. Helium goes here, same as neon and argon. Yet, neon has a valency of 8, argon has a valency of 8, neon has a valency of 2, but we put it here because he has filled up, because helium has filled up orbitals, same as neon and argon, not because of the number of valence electrons. Now, since elements in the same group have the same number of valence electrons, the chemical properties and chemical reactivity of elements in the same group will be very similar. Either they react by losing 2 electrons, 1 electron, gaining 1 electron, gaining 2 electrons, gaining 3, and so forth. So this is a summary to show you the relationship. The second period has elements with their outermost shell as 2. The third period has the electronic configuration of these elements having their outermost shell as 3. How do I know? Let me take an example of sodium and magnesium. Okay, magnesium I believe is 12, sodium is 11. Sodium is 1s2, 2s2, 2p6, 3s1. Notice the 3. That tells you the period where it's found. Magnesium will be 1s2, 2s2, 2p6, 3s2. Notice the 3. So then sodium and magnesium and aluminum, all of them will end up in the third shell. It's the same case, same process to determine why these all are in the second period. For hydrogen, hydrogen and helium, this is 1s1, this is 1s2. They are all in the first, they are all ending with the first shell, so they're in the first period. Okay, now the valency will tell you why groups are in the same column. Like I expect hydrogen, lithium, and sodium to be in the first group with only 1 valent electron. I expect fluorine and chlorine to be in main group 7 because they all have a total valency of 7 electrons. I expect neon and argon to be in the same group, main group 8a, because they have a total of 8 valence electrons with the exception of helium, which has 2, but it has a filled up s orbital, so we put it in main group A because it cannot gain or lose. That's the idea. Electron dot symbols. So usually, because we know the valency of elements, we just show the outermost electrons. So like for carbon is 1s2, 2s2, 2p2, because carbon has atomic number 6 electrons, 6 protons. The outermost shell, the valence shell, is second shell with 4 electrons, so we just show 4 dots for that. Oxygen has atomic number 8 electrons, 1s2, 2s2, 2p4. Again, the outermost shell is a second shell with total of 6 valence electrons. Those are the 6 dots you see here. 1, 2, 3, 4, 5, 6. Chlorine, I showed you, is 1s2, 2s2, 2p6, 3s2. We need to account for 17 electrons. And 3p5. Again, you are in the third period, but again, you have 7 valence electrons, which are the 7 dots you see there. And this is what we call, that drawing is what we call the electron dot symbols. The dots are really the counts of electrons, the valence electrons in this case. Each dot is 1 valence electron.